So for example 2, we're going to do the same thing. We're going to find the intervals where the function is increasing and decreasing and the local extrema of the function. So what we have to do is step 1, find the derivative of the function and then find the partition numbers. Now notice that this is just a number over x minus 1. And whenever you have a number over x minus 1, it's best to rewrite it as 5 times x minus 1 to the negative first, because here we know that x minus 1 is raised to the first power because there's no exponent there. And again, rewriting it like this lets us use the chain rule instead of having to use the quotient rule. So let's go ahead and find the first derivative. So again, this is all part of step 1. First, we find f prime of x. So negative 1 times 5 is negative 5. X minus 1 raised to 1 less, negative 1 minus 1 is negative 2, times the derivative of the inside, well, the derivative of x minus 1 is just equal to 1. So if I rewrite this, f prime of x is equal to negative 5 over x minus 1 quantity squared. Then I need to find those partition numbers, so I need to figure out where is this first derivative equal to 0, and where is this first derivative undefined. So if I set the first derivative, negative 5 over x minus 1 squared equal to 0 to solve, again, I can always put this 0 over 1 and cross multiply. Well, 1 times negative 5 is negative 5, and 0 times x minus 1 squared is equal to 0. Well, negative 5 doesn't equal 0. That doesn't make sense. So there is no place where this first derivative is equal to 0. So I'm not going to get an x value because there's no place where the first derivative is equal to 0. Well, what about where it's undefined? Is it possible for this to be undefined? Well, yes, of course it is, because this is a rational function. How do I know that? Again, because there's that fractional bar, and I have variables in the denominator. So the first derivative is going to be undefined anywhere where the denominator is equal to 0. So if I set the denominator of x minus 1 squared equal to 0 to solve for x, first I notice that I can take the square root of both sides. So the square root of x minus 1 squared leaves just x minus 1. And the square root of 0 is 0, and since 0 is neither positive nor negative, I don't need to write plus or minus 0. Now let's solve for x. Just add 1 to both sides, and I get x is equal to 1. So this is a partition number because it's somewhere where the first derivative is undefined. Now it is not a critical number, and the reason that it's not a critical number is, recall, in order for this to be a critical number, x equal 1 has to exist in the domain of f of x. But if I look here, my function is 5 over x minus 1. So it's also a rational function, and the domain of that function is all real numbers except for 1. So 1 would not be a critical number, but it is a partition number of this function. So then, step 2 now says to put these numbers, or this number, on the number line. So I'm going to stick the number on the number line. And now step 3 says that we need to choose a test value from each one of the intervals. So here I'm looking at the interval between negative infinity and 1, so I'll choose 0. And here I'm looking at the interval between 1 to positive infinity, so I'll choose the number 2. And I need to evaluate the first derivative at each one of those and figure out if the sign is either positive or negative. So f prime of 0 and f prime of 2. And we're just going to use a calculator for that. So if we were to grab a calculator, we would get, recall that first derivative is negative 5 over x minus 1 squared. So if I plug in a 0 into that first derivative, negative 5 divided by 0 minus 1 squared, I end up with a negative value. So that means that all the numbers in this interval are negative. Well, let's try plugging in a positive 2. So negative 5 divided by 2 minus 1 squared, we end up with also a negative value, which means that all the numbers in this interval are also negative. So step 3 here again was picking the numbers and then figure out whether we are positive or negative. If we're positive, we're increasing. If we're negative, we're decreasing. Now if I want to figure out where the function is increasing and decreasing, well, I know that f of x is decreasing from negative infinity to 1 and also from 1 to infinity. Now you may be tempted to say negative infinity to positive infinity, but that's not correct. We can't do from negative infinity to positive infinity, and the reason is because this number, the number 1 here, does not exist in the domain of the given function. Since 1 is not part of my given function's domain, I can't be increasing or decreasing at a number that's not allowed in my function. So for this, I would have to say that my intervals for decreasing are -infinity to 1, and then also from 1 to positive infinity. So where is this function increasing? Well, the function is increasing nowhere because it's always decreasing. And finally, do I have local extrema? That's step number 4. Step 4 is asking us to figure out if we have local extrema. Well, I don't have local extrema because our function has to go from increasing to decreasing to have a max, or decreasing to increasing to have a min, and I am not. Well, I'm going from decreasing to decreasing some more. So for step 4, I know I have no local extrema. So now I can give you a function, and you can figure out where is this function increasing, decreasing, and where it has local extrema. But let's talk about what's happening for some of these functions where the first derivative is equal to 0, where the first derivative is undefined. So horizontal tangents. You have a horizontal tangent anywhere your first derivative is equal to 0. The first 4 pictures here show us having a horizontal tangent at this letter C. So here we have a horizontal tangent at C. Here we have a horizontal tangent at C. Here we have a horizontal tangent at C. And here we have a horizontal tangent at C. Now notice, you can have minimums and maximum values. This is a minimum value because it went from decreasing to increasing, and here you have a maximum value because you went from increasing to decreasing. You can have a minimum and maximum value at any place where your first derivative is equal to 0, but it doesn't necessarily guarantee that you're going to have a minimum or maximum value, because notice here at these C's, we have horizontal tangents, but for this particular function, I'm increasing, and then I'm increasing some more. Since I'm increasing and increasing some more, I'm not going to have local extrema in this picture. And here I'm decreasing and then decreasing some more, so I'm not going to have a local extrema in this picture. So a function has a horizontal tangent when the first derivative is equal to 0. So you can have a minimum or maximum value when the first derivative is equal to 0 only if you change from increasing to decreasing for a max or decreasing to increasing for a min. Your first derivative is not going to be defined where you have cusps like this, or where you have vertical tangents, or if you are not defined so you have a vertical asymptote at that point. So let's call all these points C. Now, if you are changing from decreasing to increasing, as we are in this first picture, you're going to have a minimum value at the point C, comma, f of C. And here, since you change from increasing to decreasing, you're going to have a maximum value at the point of C, comma, f of C. But just like the pictures above, here notice you're going from increasing to increasing some more. So here you don't have local extrema. And here you go from decreasing to decreasing some more, so you have no local extrema. So these are just pictures, things that show you what it looks like where the first derivative is undefined. So please note that all 8 of these blue pictures are pictures of the graph of f of x. So you have a horizontal tangent at all of these places that I drew here. What does that mean? That means that the first derivative has a value of 0 at that C. And anywhere you have a cusp, like here, or a vertical tangent, you know your first derivative is undefined. And so this is just kind of a picture representation as to why we try to figure out where the first derivative is undefined and why we try to figure out where the first derivative is equal to 0. Because if we are going to have a minimum or maximum value, it's going to be occurring at these places. Let's use all that information to answer everything for number 3. Now number 3 is saying that the accompanying figure shows a portion of the graph of a function. So this is the graph of f that we're given here. What we want to do is identify A through H using this graph. For part A, identify the intervals where your function is increasing. Recall that means that you're going up from left to right. So notice that from here to here I'm going up, so I know that from negative infinity to a, I'm increasing. Well, from a to b, I'm going down, so that would mean I'm decreasing, which is the letter b, so I know from a to b, that interval I'd be decreasing. And then notice from b to c, I'm going up. From c to d, I'm going up. From D to E, I'm going up. And from E to F, I'm going up. So everywhere from B all the way to F, my function is going up. So I am also increasing from B to F. And then notice after F, from F to G, I'm going down. And from G to infinity, I'm going down. So then I'm decreasing over the interval from F to infinity. Part C is asking us to identify the intervals where f prime of x is greater than 0. Well, that's the exact same thing as asking me, where is my function increasing? So where is my function increasing? And where is the first derivative greater than 0 is the same thing. So the answer there should be from negative infinity to a and from b to f. Part D is asking me, where is my first derivative less than 0? Well, my first derivative is less than 0 anywhere my function is decreasing, so the answers for part B and part D will be the same, from a to b and from f to infinity. Then it's asking us to figure out what are the x coordinates where the first derivative is equal to 0. So it's asking us find the x values where that first derivative is equal to 0. That means that we're looking for horizontal tangents. We need to find horizontal tangents. We had to find the places where we're going to end up with a horizontal tangent in that graph. So if I go back to the graph, well, that's a cusp, so I know that wouldn't have a horizontal tangent. But we can have a horizontal tangent here at B. That's not a horizontal tangent. But you have a horizontal tangent here at D. Not at E, but yes at F, and not at G. So we have horizontal tangents at x equal B, x equal D, and at x equal F. Then it's asking you to identify the x coordinates where your first derivative does not exist. Where does our first derivative not exist? Well, our first derivative is not going to exist anywhere that we find a cusp or a vertical tangent. So let's figure out where I see a cusp or a vertical tangent. Well, notice here at A, I have a cusp. That's not a vertical tangent. The tangent line to C is not vertical, nor is it to E. But here at G, I do have a vertical tangent. So I'm going to have my first derivative not existing at x equal a and at x equal g. And then it's asking me to figure out the coordinates where f of x has a local max. So that's going to be any place. Remember, a maximum occurs anytime you go from increasing to decreasing, when you're going from increasing to decreasing. So notice here I'm going from increasing to decreasing, so I have a max at A, and then again I'm going from increasing to decreasing here at F, so I have a maximum at F. Last part H, is asking us to figure out where we have local minimums. And local minimums occur where you go from decreasing to increasing. So from decreasing to increasing is what we're looking for our minimums. Well, notice here at B, I went from decreasing, then my function started increasing. So I have a minimum value here at B. Here at D, notice I go from increasing to increasing some more, so that wouldn't work. Again, C, increasing to increasing some more. E, increasing to increasing some more. And at G, I go from decreasing to decreasing some more. So the only place I have a local min in this case is x equal B. So we're taking a lot of this information and trying to put it abstractly. So if I give you a function, you find the first derivative, you find the partition numbers, you stick those partition numbers on a graph, you figure out the intervals where the first derivative is positive or negative, and that tells you where your function is increasing or decreasing. You can look at a graph and figure out where your function is increasing or decreasing, or where your function has a first derivative that's greater than 0 or less than 0. You can find local extrema looking at the function. Now what I want to do is I want to give you the function. So example 4 here, we're given f of x. This is the graph of f of x. And we want to construct a sign chart for f prime of x. And then sketch the graph of f prime of x. So what do we know about the graph of f of x? So this is the graph of f of x. So let's figure out everything we know. So if I look here at this graph, this is the graph of f of x again. If I look at this graph, I know that this graph is increasing from negative infinity to negative 5. It's decreasing from negative 5 to 0. It's increasing again from 0 to 5. And it's decreasing from 5 to positive infinity. I also know that it has a horizontal tangent here at negative 5, at 0, and at positive 5, which means that f prime of x is equal to 0 at x equals negative 5, x equals 0, and x equals positive 5. Because remember, you have a horizontal tangent at the value of c where f prime of c is equal to 0. So we would have a horizontal tangent here at negative 5, at 0, and at positive 5. So let's construct that sign chart for f prime of x. So the numbers that I want to put on my sign chart are numbers where that first derivative is equal to 0 or where the first derivative is undefined. So I didn't have any place, if you look at this graph, where the first derivative is undefined. So I'm just going to place on this graph negative 5, 0, and 5, the numbers where the first derivative is equal to 0. And then anytime you see that you are increasing, you know that the value of the first derivative, f prime of x, has to be greater than 0. So from the interval from negative infinity to negative 5, I am increasing. From the interval from 0 to 5, I am also increasing. So the value of the first derivative is greater than 0. And then here I know that I am decreasing, which means the value of the first derivative is less than 0. So from the interval from negative 5 to 0, I am decreasing. And from the interval from 5 to infinity, I am also decreasing. So we're almost done. We want to label exactly what's happening at negative 5, 0, and 5 to be finished with our sign chart here. So at negative 5, we know the value of that first derivative is equal to 0. So here what we would write is f prime of negative 5 is equal to 0. Again, at 0, we know that the value of the first derivative is 0, so we would write f prime of 0 equals 0. And at 5, the same thing, so here we'd write f prime of 5 equals 0. So that is the sign chart for the first derivative. You're positive, then you're equal to 0 at negative 5. You're negative, then you're equal to 0 at 0. Then you're positive, and then you're equal to 0 at 5, and then you're negative all the way to infinity. So then it's saying, okay, use this information to sketch the graph of our first derivative. So let's go ahead and sketch f prime of x. Now what we know, again, is that f prime of x is equal to 0 at negative 5, at 0, and at 5. So those are considered x-intercepts. So these are my x-intercepts. So I will cross the x-axis at negative 5, at 0, and at positive 5. If the first derivative is positive between negative infinity and negative 5, that means that it has to exist above the x-axis. If the first derivative is negative between negative 5 and 0, that means that it has to exist below the x-axis. You just need to connect your dots. If your first derivative is positive between 0 and 5, that means that it has to exist above the x-axis. And finally, if your first derivative is negative from 5 to infinity, then that means that you need to exist below the x-axis. So this is a graph of f prime of x. This is telling us I exist above the x-axis, below the x-axis, above the x-axis, below the x-axis. And it's a graph, not the graph. So there's lots of different ways that we could have drawn this, but this is a sketch of the graph of the first derivative.